So now we are going to discuss some of the important parameters that we need to know about packed beds before we discuss the equations that we are going to cover in this course or in this part. So one of the very important parameters that we need to know about any packed bed or solid particles in general, whether it's for packed beds or for any other applications. I mean, we use it for even for storage of solid particles or for any other application that includes solid particles. This parameter is called the porosity or the void fraction. So any bed, no matter how size or what is the size of the particles that we have in this bed, will consist of two phases: the solid phase and some spaces between them, which is called the voids. The solids is not filling the whole space. It's going to fill part of the space, and the other part is the empty space. And in case of packed beds, this is very important because this is the volume where the fluid is going to flow through. And the volume that's occupied by solid particles will be denoted as V solids, which is the dark regions here, and the volume that's occupied by the spaces or the empty space between the particles, we call it V space. And the total bed volume is going to be the sum of both, which is the total volume that we see. It's going to be the sum of both the volume of solids and the volume of the space. And the fraction of the total volume that's occupied by space is called the void fraction. And I think that the name is very clear. It's the fraction of the volume that is void, which is empty, or sometimes called the porosity. And we give it the symbol epsilon. And this is important not to be confused with the surface roughness that we discussed in chapter 8. The surface roughness is also denoted by epsilon, but it's a totally different parameter. So here the porosity is epsilon, which is the volume of space over the total volume of the bed. The volume of space is the volume of the bed minus the volume of solids from here. Okay, volume of bed minus volume of solids is the volume of space. So we can define the porosity as 1 minus volume of solids over the volume of bed. Okay, so this is the percent of the volume occupied by the solids. So it's 1 minus this is, which just makes a lot of sense. Of course, epsilon is going to be dimensionless quantity because it's volume over volume, and its value is definitely less than 1. Theoretically speaking, it's from 0 to 1, but it's never 0 and it's never 1. If it's 0, then it's totally solids. If it's 1, then there are no solids, so it's going to be somewhere in between. And based on this, we can define a new parameter which has to do with the density. So now we have two types of volumes that we have when we deal with the solid particles. We have the volume of the solids, just the volume of the solids, excluding the spaces between them. And we have the volume of the bed itself. Okay, the volume of the bed, which is the total volume, which we can easily measure, because if you have a bed, let's say it's a cylindrical column that has a diameter of 1 meter and height of 1 meter, for instance, it's very easy to calculate the total volume. It's area by height of the bed, and this is all, and you're done. So this is sometimes more convenient to deal with or to measure, or I mean to calculate, which is the volume of the bed. So that's why we have two volumes when we deal with the packed beds: the volume of the solids by themselves, or the volume of the bed that they are put in. And based on this, we have two densities based on which volume we are focusing on. So we have the bulk density, which is the mass over the whole bed volume, okay, which is easy to measure. And we have the particle density, which is the mass over the volume of solids. Of course, when we calculate this density, we should include the total mass of the bed, but usually the solid particles are much more denser than the voids or the space density. It's air. The density of air is 1 kilogram per meter cube, and the density of the solid or the solid particles is maybe 3,000, 4,000 or something like this. So it's like 1,000 times more dense. That's why the mass that we have here, theoretically speaking, should be the mass of the particles and the air, but the mass of the air in between is very, 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 very negligible. So we take the mass in both cases to be the same. So the mass of the particles here is the same as the mass of particles here. So we have the same mass, but different volumes, which is the volume of the bed and the volume of the solids in case of particle density. And we can find the relation between the two of them if we do, and of course, the volume of bed is more than the volume of solids. So the density, the bulk density is less than the particle density. Okay, so this is something that we need to keep in mind. Now we can get the relation between these two densities. If we divide these two densities, the bulk density over the particle density, we get the volume of solids over the volume of the bed, which is 1 minus epsilon. If you remember, if you go to the previous slide, epsilon is 1 minus V solids over V bed. So if we, this is V solids minus V bed, which is 1 minus epsilon. Or we can say that epsilon is 1 minus rho bulk over rho particle, or rho bulk is rho particle times 1 minus epsilon, which is the same thing. So it's it's easy to get or to calculate the bulk density if we know the particle density and the porosity, or to calculate one of them if we know the other two. Now let's go to the important point here, which we are interested in, which is the pressure drop in packed beds. This is one of the very, very critical parameters that we are interested in when we study packed beds, which is how much pressure drop the fluid will have when it passes through this solid bed. And the reason is the flow through packed beds is very, very and it's not as smooth as it is in case of the pipes or tubes, the empty pipes and tubes. And the reason is the fluid that is flowing is not going in a straight line. It's going through a very, very irregular path. It goes sometimes through very narrow parts, and then through wide parts, and then to very small areas. So it passes through a lot of sudden expansions and sudden contractions, beside a lot of change in direction. So this is a lot of losses that the fluid will have to or a lot of energy losses for the fluid while it's going from one, or while it enters the bed until it leaves from the other side. So the pressure drop is going to be very high, and it's a very, very critical thing, and it's very important to know how to measure or calculate this pressure drop, because this has very big impact on the performance of the or how you're going to operate the column or the bed. It will affect the compression power or the pumping power that you need to give to the fluid, and this is translated into money. So this is how much money you want to put in the pump that you are going to use, and also in the operating cost. It's not just the how expensive or cheap the pump is, it's also how much money you're going to put in operating this pump. So this is very important to know how to measure the pressure drop. Besides this, that it's one of the key parameters that we use to tell how well the bed is operating. If there is any issue, the very, very first thing that tells us that there is an issue or a problem with the operation is the pressure drop. Whether there is a blockage, if there is part of the bed that is broken and it's not allowing the flow to be as it should, any problem will be easily showing up in the pressure drop. So that's why pressure drop is very, very important when we operate the column. The equations that measure the pressure drop or are used to predict the pressure drop of packed beds are many. There are many equations, and one of the very, very famous of them is Ergun equation. Ergun equation is one of the equations that is very, very famous, and it's used in many cases. And it is as follows. Usually, and this is one thing you need to know, that the equations that are used to calculate or to predict the pressure drop or the head losses in packed beds are mostly empirical equations, meaning that they are not like what we said before, that it's based on theoretical basis and it's derived. No, it's not how it's it's produced. It's produced experimentally. Like there are a lot of experimental tests that have been made, and the results have been fitted with this equation. And we will see some of the implications of this on the equation that we see. So this is the equation that we use for head losses. The epsilon is known, it's the porosity, L is the length of the bed, the G is acceleration due to gravity, of course, and U node is the fluid superficial velocity. I mean, this is one of the implications of these empirical equations. The velocity that we should use, theoretically speaking, the velocity that we should use is the velocity inside the bed, because this is where the losses are taking place. But it's almost impossible to know what is the velocity, because it varies from point to another. And maybe at one point there is a lot of spaces here, and then it gets very narrow here, so the velocity will vary from a point to another. So it's not practical to use the velocity inside the column. So we are using the velocity, which the superficial velocity, which is the velocity based on the total cross-section area of the column. Okay. Assuming that the column is empty. This is not the actual velocity, but we are using this velocity because there is no other means we can use the actual velocity, and because the equation was fitted on this velocity, meaning that when they did the experiments, they fit the data with the superficial velocity. So we have to use this velocity because this is what was used to produce the equation. So the superficial velocity is the volumetric flow rate over the total area of the column, which is pi over 4d squared. This is the diameter of the whole column. Okay. And this is the diameter of the column. Now we have the dP. dP is called the effective particle diameter. So if we have spherical particles, then the particle diameter is the diameter of a sphere. But as we said before, there are a lot of different shapes. None of them is spherical. So if we have non-spherical shape, we use what we call the effective particle diameter, which is 6 over AV, and AV is the specific surface area of the particle, which is the total external surface area of a particle to its volume. So it's the area of the particle over the volume of a particle. And this is the AV. So this has units of meter power -1, and here it will have units of meter. It's 6 over this. So for any shape, we can find the particle, the effective particle diameter of it. The last term that we have here that we haven't discussed is the friction factor, which is FF, which is the friction factor in packed bed, and it is calculated as follows. It has a part here that is used for laminar flow, or the laminar part, and this is the turbulent part. Okay, so if it's and it's easy to understand this. If it's laminar flow, then Reynolds number is very low, so this means that this term is going to be large compared to this. So this is going to be the dominant term. If it's turbulent flow, then this term would be more than 4,000. So this whole term would be very negligible compared to this term. So it's valid for both, for laminar flow and turbulent flow. It takes both into account. Okay, and Reynolds number in this case, it's defined as rho u node dP over 1 minus epsilon u. So again, this is not the regular Reynolds number we're used to use before. This is the superficial velocity, and this is 1 minus epsilon, which is the porosity. So these are the equations that we have. So if we put everything together, this Reynolds number in here, and we plug this friction factor with Reynolds number in here, then the equation will be this nice looking equation, which is kind of long equation, but it's very, very straightforward. I mean, there is nothing complex here. You can just substitute directly to get the head losses if you know all the terms that we have here. So by rearranging the equation, it will look like this. Okay, and again, this term represents the laminar, the flow losses, and this term represents the turbulent flow losses. So this is the equation that we use for the head losses. Now we are interested in the pressure drop. So if we want to calculate the pressure drop, we can apply Bernoulli equation between the entrance of the bed and the exit of the bed. And if we apply Bernoulli equation, there is no pump or turbine here, of course. So we'll have the three terms for the pressure, velocity, and elevation, and we'll have the head losses. And the area here is usually the same as area here, so the velocity terms will cancel out. And we want to find the pressure drop, which is P1 minus P2. So it's going to be Z1 minus Z2 plus HL. This is delta P over rho G. And we can plug in the formula for HL that we had from before. And this is the equation that we have. Okay. So it's still the same equation for H losses plus delta Z. If we have gas flow, usually the pressure due to the fluid head is very, very negligible. Or if we have a horizontal pipe, if this pipe is horizontal, then Z1 is equal to Z2, and so the term delta P can be just what is between these brackets. So this is the equation that we use. This is more general, and this is kind of special case if it's gas flow or for horizontal pipes. So this is the equation that we're going to use for pressure drop calculation. So I'm going to stop here, and inshallah next time we're going to solve an example on this equation. So I'll see you then inshallah.